All right, we're recording. So we are going to do 11-4 today, this morning. It begins on print page 474, kind of in the middle, and on Braille page B474 in volume 43. Are you all there?
Mm-hmm.
Okay.
Mm-hmm.
Grab a marker. All right. So this section's about inscribed polygons and relationships with chords that are the same distance from the center. And that's what most of it's about, is realizing that if two chords are the same distance from the center, then they're going to be equal.
Oh, okay. Yeah.
Yeah.
She's always here, but
So the first picture at the very bottom of 474B is a picture of an inscribed polygon. An inscribed means that it's inside the circle. Inscribed, inside. And an inscribed polygon means that each vertex touches the circle. So notice that this square or rhombus touches the circle at point B at the top. They've got little arrows going through it, just kind of showing that we would have this perpendicularity from the center. You can kind of ignore that at first. It's showing how you could do it with a construction.
I don't like these random lines.
I know, they're random, aren't they? And then there's a diameter going directly across from A to C. That's from 9 o'clock to 3 o'clock. And then basically a diameter where they've extended the line from B to D. So they're showing diagonals of this rhombus or square. It's actually a square, isn't it?
Something.
And this is in its circle P. Okay, you make that out. So this is showing an example of an inscribed polygon. And that means that every vertex lies on the circle. So A, B, C, and D all lie on the circle. It's called inscribed. And then it's also called circumscribed because the circle goes about it. So those are interchangeable, like the circle is circumscribed about the square, or the square is inscribed in the circle, okay? That means the same thing. And the biggest thing to remember when you're recognizing these is that every vertex has to touch the circle, okay?
yeah.
That was one point they wanted to make in this section. Not the biggest point of the section, really. If we turn a couple pages, we actually want to talk about Theorem 11 dash. So I want to be on A479. Or 5, excuse me, A470. Oh, nope. B475. So get yourself all the way to B475. And I want to talk about the Theorem 11-6. This is the meat of this section, okay? So take a look at this circle. We got this nice sizable circle in the middle of our page. Nice sizable circle, yes. And it's circle P, that's our center, and there's some stuff going on within this circle. There's two chords. So from A at about 10 o'clock to D at about 5 o'clock, there's a chord. You got that one?
Mm-hmm.
Okay. And then if you go to just past 12 o'clock at point B, and you go down to point C at about 4 o'clock, they're not touching, they're apart from each other, but they're chords, right? BC is a chord. Now, what's really cool about this theorem is that if you go to the center and you notice there is a segment, a little tiny segment perpendicular to AD and a little tiny segment perpendicular to BC from center P. So it goes PL, that's the one on the left that's perpendicular to AD, and PM is the one on the right that's perpendicular to BC.
What is the L?
L is on the intersection point of AD where the little square is. You got it?
Yeah.
Okay. So what this is showing is that if you have two lines, two chords that are perpendicular, or two little segments that are perpendicular to these two chords, and they're congruent, then the chords are congruent. In other words, if chords are equidistant from each other, they're congruent. Okay? So this is showing that with this little drawing. And so this is Theorem 11-6. If you go up above the circle, let's read it in words. It says, in a circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. And in symbols down below, it says AD is congruent to BC if and only if LP is congruent to PM. So if those two little guys in the center are congruent, if they're X value and X value, or 10 and 10, or 2.8 and 2.8, then we know the chords are congruent. So we always want to just put that to memory. It's a really cool thing. Right? Because they're equidistant from the center. They're the exact same distance from the center. And so in order to do that, they have to be congruent. Okay? All right. So we use that theorem in order to do a bunch of basic kind of algebra link style problems. So next page is our first problem to do, and it just brings forth basic algebra skills. That algebra doesn't go away. It's going to ramp up next year. All right. So in example 2 on page C475, we have another circle. So good practice today of making out these tactyls and circles. So make out your circle. The center is labeled A, just above it. We have two chords that extend, one down from the 12 o'clock position to about the 8 o'clock position. That's chord RP. And then one chord on the other side that extends from R to Q at about the 4 o'clock position. Okay? All right, and notice in the center, there's two little segments that are perpendicular to our chords. They've got little perpendicular indicators. And they are each X values. So that means if they're both X, they're both congruent, correct? Yeah. So don't, it could be 2 and 2 or 5 and 5. They just said X and X. So you would know that those are both equal. So your brain goes, aha, if those are both equal, then I know RP is equal to RQ. It's congruent to RQ. Those two are going to be the same. So now I'm going to look at question number 2 and see what they want me to do. So directly above the circle, it says, in circle A, PR equals 2x plus 5, and QR equals 3x minus 27. Find x. So, yeah, exactly. Abby's saying very quietly, I wish she would speak up. She only speaks up when she's mad at me. So basically, RP equals RQ, right? So we substitute in the values they gave us. Oh, I lost Bryant. Is Bryant still there?
Yeah.
Oh, okay. Sorry, Brian. I thought you weren't. Okay, good. All right. 2x plus 5 equals 3x minus 27. So I'm writing that down on my whiteboard. 2x plus 5 equals 3x minus 27. So this is a basic, multi-step, single variable algebra problem you've been doing all year, right? So we want to get our like terms, so we're going to do minus 2x from the left, so minus 2x from the right. We end up with 5 equals x minus 27. I'm going to add 27 to both sides, right? And then x equals 32. Done. Okay, and all they wanted to know they just wanted to know what x equals. They didn't care about what the size of the segment was. If they asked what the size was of the segment, we're going to plug it back in, aren't we?
Yep.
All right? Yes.
I have on my backpack in the computer lab, and I didn't have my chocolate money.
Uh-oh, better go get it. All right. Okay. Turn the page to the next page. That just shows the proof, right? Going through each step that we just went through if you were having to explain what you did. PR equals QR, and we get to say that by definition of congruent segments, or you could say Theorem 11-6, or you could say if you've got two segments that are equidistant from the center, they're going to be equal to each other. We use the substitution property, 2x plus 5 equals 3x minus 27. They subtract 2x from both sides, and they say subtract 2x from each side. That's subtraction property of equality. Simplify, 5 equals x minus 27. Add 27 to both sides using the addition property of equality, and 32 equals x. Right? All right, let's do it again on the next page. So 475E, 475E. Find that. Got another circle. Let's explore that. Make sure we understand what's going on here. So we have a circle, and the center is labeled O. There's two chords. There's one at about 11 o'clock labeled R, and it extends down to about 7 o'clock or 8 o'clock, more like 8 o'clock, at C, and C's braille is a little funky. It might run into the circle on you.
Yeah, it does.
And then on the right-hand side, point S at about 2 o'clock extends down to about 5 o'clock at point T. In the middle, there is a segment that goes from O to the left, perpendicular to our chord RC, and it intersects at point A. And from the center to the right, there's a little segment that's perpendicular to our chord ST that intersects at point B. Now, there's nothing on the graph, on the graphic, on the tactile that shows us that O to A and O to B are equal. But in words, I think it's giving it to us up above. So let's look at the your turn in the words, and it says in circle O, O is the midpoint of AB. So the center is the midpoint of the section AB. So your brain should go, oh, well, if it's the midpoint, then I know that A to O and O to B are equal, right?
Mm-hmm.
It's tapping into that knowledge from prior sessions. So we do know that RC and ST are equidistant from the center O. So if they're equidistant from the center, then they are congruent. So we know RC equals ST, right? E475. All right, so it says if CR equals negative 3x plus 56 and ST equals 4x, find x. So we're just going to do what?
Make them equal.
Make them equal to each other. No problem. Piece of cake, right? So we just got to be careful with our negatives. That's where gets tricky. So we have negative 3x plus 56 equals 4x. So negative 3x plus 56 equals 4x. What would we like to do with that?
I would get rid of the negative.
Add 3x. Yeah, we got a negative 3x, so we want to add 3x to both sides. So we end up with 56 on the left side equals 4x plus 3x, which is 7x. Now we're just going to use our division property of equality. Divide by 7 on both sides, and x equals 8. Okay? So piece of cake. Just being careful with writing out the equation carefully, right? And watching those negatives. The little teeny tricky part on that one is they tossed in a negative 3x on you, and they want to make sure you notice that. All right? So not too bad. Turn the page. Let's see what they got on the next page. They've got some practice on the next page. I want to talk about some of these, and then we'll do a couple more problems like we just did. Number 1 says to look at the pattern in the inscribed polygons, and what would a polygon with 200 sides look like? So notice that the first circle, the inscribed polygon, is 3 sides. It's a triangle. The next circle, the polygon, has 5 sides. How many sides is a polygon with 5 sides? What's the name of it? Pentagon. Good. The next one has 6 sides in the hexagon, and notice what's happening now with it to the circle, right?
Mm-hmm.
The next one, actually there is a circle going around this, and it looks like 8 sides, not the easiest to make out. It's an octagon. So what would be your prediction if we had 200 sides? What would it look like? What's happening and going from 3 sides to 5 sides to 6 sides to 8 sides? What's happening with the sides in the circle?
We're adding up.
They're adding up, but how is it feeling? What does it feel like? The octagon next to the circle, what does that feel like compared to the triangle next to the circle? In the circle.
Bigger. Getting bigger.
It keeps getting closer and closer and closer to this circle edge, doesn't it?
Yeah.
So unless we could make a really, 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 really massively big circle like out on the track to show 200 sides, if we crammed 200 sides into this little circle, we wouldn't be able to even tell the difference. It would start looking like a circle. All right? Now, it's technically not a circle. It's still a 200-sided polygon, but to the feel, to the eye, it looks like a circle. The more sides you get, it starts to look like a circle. So that's what they wanted you to think about. Okay? All right. Number 2, down below this, number 2 says, compare and contrast the meanings of the terms circumscribed and inscribed. What do those mean? Circumscribed and inscribed. Inscribed is inside. Circumscribed is the circle on the outside, right? And what is the definition of an inscribed or circumscribed polygon? What is the biggest thing what is the number one thing that has to happen in order to say that it's inscribed or circumscribed?
It has to have a different shape.
Different shape, okay.
Shape inside, like that.
Right.
Wheel.
But I could throw a square on the inside of a circle and just have it hanging out there floating around.
The vertexes have to touch the circle?
Yes, Bryant. The vertexes have to touch the sides of the circle, or the edges of the circle, right? Okay. That's what I was looking for. Because you could have a circle and a little square in there floating around. It's not inscribed. Inscribed means it's touching the circle at each vertex. Okay? All right. We're going to skip number 3 and go to number 4, which we like number 4. This was the transcriber that really liked to make tactyls the way they should be made. There was this one, you can tell throughout this book, there is this one person that did tactyls that they were these really large tactyls, weren't they? So you have a big circle that takes up the entire page practically. Isn't that awesome?
Mm-hmm.
I know, I wish I knew who that was. I would send them a thank you note.
Yeah.
They knew what they were doing.
Mm-hmm.
I wish they would have given lessons to everyone else. Okay, so we have a big, huge circle. This is number 4. It says in circle T up at the top, it says CD equals 19, find AB. So we have circle T, we have a center T. We have 2 chords. One's coming from about 10 o'clock at point A down to about 6 o'clock, point B. A to B. There's another chord on the other side from about 2 o'clock at point C back down to point B again. Okay?
Mm-hmm.
From the center are 2 segments, one to the left, going to intersection point E. It has a right angle indicator and a tick mark. And then on the right, from point T to our chord, CB, it intersects at D. It has a right angle indicator and a tick mark. So we've learned what? If we have from T to E and T to D that are the same, what is the relationship of AB to CB?
They're going to be the same.
They are the equal. All right, so we turn our brain on for that. Now we go back up and read the information again. In circle T, CD equals 19. So let's go find CD. So we go back down to our circle, and C is at 2 o'clock, and D is the intersection point. CD is 19. Find AB, and that is on the other side from 10 o'clock to 6 o'clock. Yeah, we got to find AB. They've given us CD is 19. What is AB?
It gotta be 38.
Say it loud and proud, Abby. It's got to be what?
38.
38. Why is it 38, attorney?
Because it's CD is 19
Uh-huh.
and halfway from D to
Oh, that's a
B.
midpoint. I see.
B has to be
19.
also.
All right, so together.
And since they're congruent
Mm-hmm.
from A to B
Uh-huh.
has to be 19.
Well, 19 and 19,
19.
yeah, or 38. Good, excellent. That was a very good argument, Attorney Griffith.
I was
All
going to say 19.
You were going to say 19. Thanks for being honest, Attorney Spong. You would have been wrong. All right. The biggest deal is to notice that that was a perpendicular bisector. Remember, you learned a couple sections ago that if you have a perpendicular line from your center, it bisects your chords. And so Abby knew that CD was half of CB. So CD was 19, DB was 19, so the entire CB is 38. And then that's congruent to AB because they're equidistant from the center. Right? All right, good. Let's turn the page. The same tactile maker got assigned 2 pages in a row.
Yeah.
Yay! All right, number 5. Huge circle again. Make your way around this big old circle. Takes up almost the whole page. We got a center R. Find that. And just past 12 o'clock is point B. And that goes at an angle to about 8 o'clock at point A. So we have a chord AB there. And then at about 1 o'clock is point C. And it goes straight down to about 4 o'clock at point D. More like 5 o'clock. All right. And then from the center, there are 2 segments that are perpendicular to each chord. And they have labeled those X, each X. So that means that X and X means X equals X, right?
Mm-hmm.
So they didn't use a tick mark. They chose to use X units, which is the same thing. All right, so our brains are turned on, and we know from that theorem, 11-6, if we have 2 chords that are equidistant from the center, we know they're congruent to each other. So let's read what they want us to do in number 5 directly above the drawing. It says, in circle R, if AB equals 2x minus 7 and CD equals 5x minus 22, find x. So we double check and make sure they're not tricking us with half of the chord, right? So A to B. Okay, yep, we got the whole thing. AB is 2x minus 7. And C to D, okay, the whole thing. C to D is 5x minus 22. So how are we going to solve this?
Make them equal.
Make them equal, yeah, piece of cake. We just got to do some work with our algebra, which is good practice. So 2x minus 7 equals
5x minus 22.
Good. All right, I'm writing that down on my whiteboard. You can tell me what to do. 2x minus 7 equals 5x minus 22.
Subtract 5x from, or 2x from.
Yeah, I think I'd do the 2x to make my life easier. So subtract 2x from the left and the right. Okay, so that cancels out on the left, and we're left with negative 7. Watch that minus 7, right? Negative 7 equals 3x minus 22. So negative 7 equals 3x minus 22. No. Add? What do you want to add?
22.
Add 7? I don't think so. 22, yeah. You could add 7, but you're going to make a mess. You'd end up with 0 over there and then have to move over again, right?
Oh,
That's an extra step.
7.
Yeah, so negative 7 equals 3x minus 22. We want to work with the side with the 3x, right? So 3x minus 22, we want to add 22 to both sides. So we get 3x equals negative 7 plus 22. 15. Good. 15 equals 3x.
Oh.
Divide by 3.
Divide by 3. X equals 5. And all they asked us was what's the value of x, right? Yep, find x. Okay, if they would have asked us the measurement of the chord, substitute it back in. Okay, good one. Let's see what's going on the next one. It's weird on purpose because it's a picture in the book of the end of a log. So a tree has been cut down and we're looking at the end of it.
Wow.
So it's almost a circle. It's not perfect, but it's very close. So that's what the picture is kind of, you got to visualize it's this kind of wiggly circular shape, and then they have this rectangle inscribed inside of it, all right? And it's a dotted line. Where'd my pen go? There it is. All right, so we got this wiggly little circle because it's showing kind of the outside of our log. First time I saw this drawing I hadn't looked in the print book, and I was like, all right, I'm sorry, but I think somebody that made this tactile had a little too much to drink. What is going on here? You go from the previous picture with this beautiful big circle, and then we turn the page and we have this wiggly circle. I'm like, what 3-year-old made this tactile? Right? Okay, but then I looked at the book and went, oh, I see what it's trying to do. It's trying to look like the end of a log, which isn't actually a perfect circle, but it's very close. So let's read the story problem above it. Notice also I make out that you have this kind of rectangular shape inscribed inside of it, right? And then they're going from the center and they have a heavy dotted line all the way to the outside. And they have an arrow down at the bottom, a little arrowhead, and it says 1.15 times the radius. All right, so that's the information they want us to have. But let's read the problem and see what we get out of the problem. We probably don't necessarily need the graphic. So it says the strongest rectangular beam that can be cut from a circular log is one whose width is 1.15 times the radius of the log. What is the width of the strongest beam that could be cut from a log 6 inches in diameter? Okay, so what the deal is in logging, apparently, they chop down these trees, and if they want to get a big, huge beam out of it in order to have something really strong to build like a roof or something from it, the biggest beam they can make is 1.15 times the radius. That's what they're going to cut because they've discovered that's the strongest piece. So they're telling us the diameter is 6 inches. How are we going to solve this problem to figure out the width of our beam? The diameter is 6 inches.
No, 3.
So the radius is half of that. That's right, Abby. So 6 divided by 2, our radius is 3.
3.
Okay. And then what are we going to do with that? 3 times...
1.15?
Yep, 1.15. That's it. That's all we got to do. All right? So we really didn't need the picture, did we?
Mm-mm.
It was just a little extra. It was like eye candy, I guess. All the information we needed was in the story problem. So sometimes this is a really good example of remembering that. Like, you take a look at a picture and then you go back and read and you go, oh, well, I don't really need the picture. So I'm not going to worry about the picture anymore, and I'm just going to focus on the information from the story problem. And they told me strongest board is 1.15 times the radius. They tell me the diameter is 6. I've got all the information I need. I'm going to go. So 6 divided by 2 is 3. 3 times 1.15 is 3.45. Done. All right?
Mm-hmm.
So it's a good reminder. We've ran across that a lot. You will run across that on the end of course exam. You'll have a drawing or a graphic, and you'll take a look at it, and you'll figure it out, and then you go read the problem, and you'll be like, gee, thanks. I didn't need the stupid picture, right? So just put the picture out of your mind and focus on the words. Sometimes, though, a lot of the information comes from the picture, so got to make that out. All right, let's turn 2 pages. Let's practice one more of these. Hello, Mr. Lowry.
Hey, just wanted to give you a heads up. I asked Tony if I could steal him for the first part of next period for a
Okay,
little while.
no problem.
If he forgets and comes over here, will you send him my
Send
way?
them your way. All right.
Thanks.
Okay, we have a circle. Clearly, a new tactile graphic maker made this one, but it's not too bad. All right, we're on F476. Take a look at our circle here. It says we're going to use this circle P to find X for the next, looks like 5 or 6 problems. So let's get really familiar with it. A circle, our center is labeled P right below it. There's 2 chords. B to A is on the left side, running from about 11 o'clock to 7 o'clock or 8 o'clock, about 8 o'clock. And then on the right side is a chord running from about 1 or 2 o'clock down to about 4 or 5 o'clock, straight down to D. And from P, there are 2 segments that are perpendicular to each one of the chords. And they've labeled those X units each X units. So brain kicks in. I know what that means, right? That means AB is congruent to DC. That's what your brain should be thinking, okay? So you've made that drawing out. You go, I got this. No problem. So let's go read what number 9 asks us to do down at the bottom. AB equals 2x minus 4. CD equals x plus 3. All right. No big deal. What do we do?
Make them equal.
Make them equal. Yawn. Right? We're getting good now, aren't we? All right. 2x minus 4 equals x plus 3. What shall we do with 2x minus 4 equals x plus 3?
Minus some x.
Minus the x from both sides. Good. So we have x minus 4 equals 3.
Minus 4 equals 3. So minus or plus the 4.
Yep. X equals 7. Good job. There you go. Done. Now, obviously, we're just talking about these. You're doing them in your head. You know how to do these. You would put them out on paper, right? Or put them in your Braille note and do your work to them and be very, very careful. So all the rest of the questions are just doing that. They're making one side equal to the other side and practicing your algebra skills. Pretty basic stuff. Okay? That's this whole section, really. right? It's all about that. Okay? So that's 11-4. The biggest deal is the difference between inscribed and circumscribed. They're the same, but a different way of saying the same thing, and that the polygon has to, all the vertexes have to be touching the circle. And then any chord, any two chords that are equidistant from the center, they're always going to be congruent. Always, always, always. So that's important to remember, because then you can utilize that information to find and prove other things later on. All right? What I'd like to do for the rest of the lesson in the next 5 minutes is I want to practice a problem like what I sent in the review yesterday about solving for an equation of a line if you have a slope and a point. So I'm just going to make one up. If we have, if we have a slope, our slope is, let's say 2/3. So our slope is 2/3, and we have an x-intercept of 5. Right? So those are the two pieces of information we're given, and we have to write an equation of a line.
Y = mx+.
So we're going to do something